Yeah, you may start. Okay. So today we will discuss the Elizabeth's rule and Taurus theorem. We have seen already if the limit of the function f(x) when say x tends to say suppose a is our x tends to say c is say a, and limit gx when x tends to c is say suppose b, then if b is not equal to 0, then one can find the limit of the f(x) by gx when x tends to c, and basically this is equal to the a by b. Okay. But if suppose in case a is also 0, b is also 0, if b is 0, a may be anything, then also we can discuss something, and it is shown that if the limit of the derivative exists, then this must be say 0, and in case if this b is 0 and a is less than 0, negative, minus infinity, and b is 0, a is positive, then limit will go to the plus infinity. Now, the case when a and b both are tending having the limit value with 0. So, when you consider the limit of the function f(x) over gx when x tends to c, it comes out to be 0 over 0 form, which is known as the indeterminate form. Indeterminate form. Why indeterminate? Because you cannot say the value of this is 1, or value is some finite number, or value does not exist. In fact, 0 over 0, it may exist, value, the limit may exist, limit may not exist also, and like this. For example, if we take the function f(x), say alpha times of x, and gx say x, and choose the limit c as 0, then obviously limit of f(x) as x tends to 0 is 0, which is the limit of gx when x tends to 0. Both are coming to be 0. So, when you take the limit of f(x) over gx as x tends to 0, then in fact this is coming to be, if you take the limit of f(x) over limit of gx, then it is basically coming to be 0 over 0 form. But if I substitute the value f(x) in gx, then the limit will come out to be alpha, because x will get cancelled and x is independent of any x. So, limit will come out to be alpha, a real number, where alpha is a real number. So, it means the limit of this 0 over f(x) by gx when it amounts to be the 0 over 0, then it may exist and may have a value real number, or sometimes may not exist also, that we will take some example where the limit does not exist in the case. Okay. Say for example, limit does not exist. Suppose I take another one, f(x) equal to x sin say 1 by x, and gx is equal to x. So, if I take c equal to 0, then both the limits f(x) when x tends to 0 is 0, limit gx when x tends to 0 is also 0. But when you take the limit of f(x) by gx as x tends to 0, it is coming out to be the limit of sin 1 by x when x tends to 0, which does not exist. So, in the initial form it is 0 over 0 form, but basically the limit does not exist. So, that is why to evaluate such cases, to find the limit of f(x) by gx when it amounts to be 0 over 0, then we require some rules, and that is given by the L'Hospital. Now, one more thing, here we are choosing the limit even if f of c is 0 or g of c is also 0, then in that case limit of f(x) by gx when x tends to c is also in the same form 0 over 0. It takes this form, which is also indeterminate form. So, if the function is defined at the point c, limiting point, and if it is coming to be 0 over 0, then the limit of f x over g x to calculate the limit becomes a problem, or even the limiting value is also coming 0 by 0, then it is also we cannot use any limit rules for the limits. That limit of the rational function is the limit of the numerator over limit of the denominator, which we cannot apply here. So, in such cases we require some concepts, and that is to how to evaluate this limit of this ratio when it is coming to be 0 over 0 form, and that is given by the last test. So, before going to last part, there is one we will say the indeterminate forms. Is the 0 over 0 is the only indeterminate form? No, there are many cases which are considered as a indeterminate form. So, let me say the indeterminate forms. These forms are, first form is 0 over 0, infinity over infinity is also considered to be indeterminate form, 0 into infinity, that is if f x tends to 0, g x tends to infinity, then f x into g x, this limit will go to 0 into infinity form, or f x by g x if g x also. Then 0 to the power 0, if f x tends to 0, g x tends to 0, then limit of f x to the power g x, this, okay, when x tends to c. If it is coming to be 0 to the power 0, then it is also considered to be the indeterminate form. 1 to the power infinity will also be taken as indeterminate form, and infinity to the power 0 is indeterminate form, infinity minus infinity is also an indeterminate form. So, there are various types situation where we can say the limit the forms which you are getting is an indeterminate form. To evaluate this type we require certain tricks, okay? Because just by substituting the value or taking the limit we cannot say the limit is correct, okay? Or we cannot evaluate the limit also. So, before going for the last task, let us see the one result which only requires the concept of the derivative and nothing more. What this result says, let f and g be defined on a closed and bounded interval a b, and let the value of the function at the point a is 0, value of the function g at the point a is also 0, and let g x is not equal to 0 for a less than x less than b. Now, if our f and g are differentiable function, at a, and if g prime a is not 0, then the limit of f over g, then limit of f x over g x when x tends to a exists and is equal to f prime a over g prime a. So, this is the result. Now, here in this theorem we have assumed the function f and g both are attending the value 0 at the point a. So, when you take the limit of x over f x over g x when x tends to a, basically it is of the form 0 by 0. Okay. But what this theorem says, if f and g are differentiable at the point a, and if the g dash a is not 0, then this indeterminate form has a value and equal to a prime a over g prime a. Okay. The proof of this follows like. Okay. Now, since f a and g a both are 0, So, we can write it f x by g x for x. So, for x lying between a and b, we can write f x by g x x f x minus f a over g x minus g a, because these two values are zeros. Okay. And this can be written as f x minus f a divided by x minus a, because x is strictly greater than a I am choosing. So, the denominator is non-zero, g x minus g a divided by x minus a. Now, if we take the limit as x tends to a. So, when you take the limit of this as x tends to a, x tends to a, f x y g x, we are assuming here the limit a. Okay. Even we can take the limit a plus, because we are not considering the function, simply we are taking function is differentiable at a. Okay. And then g prime a 0, define and differentiable. So, let us take the a plus here, okay, that is equal to this. So, we take this a plus in that case f x over g x is the limit of x tends to a plus f x minus f a over x minus a divided by g x minus g a divided by x minus a. So, limit of the ratio is the ratio of the limits. So, we get this goes to a prime a, this goes to g prime a, hence the result follows. Okay. So, but here we cannot dilute this condition. The condition is must that the value at the point a both must be 0. So, this we cannot dilute. So, as a remark we can say we cannot dilute the condition that f a equal to 0 equal to g a. Suppose we have a function where the values are different and not equal to zeros also. For example, if we take the function f x which is equal to say x plus 17, g x which is say 2 x plus 3, then obviously f of 0 is 17, g of 0 is 3. Okay. So, f x by g x, when you take the limit of this x tends to 0 plus from the left hand right hand limit, then it comes out to be 17 by 3 is nothing. Okay. But when you take the limit derivative of their limit as x tends to 0 plus, then derivative here is 1, here is 2. So, if this comes out to be half. So, basically both differs. The reason is because we have diluted this condition. So, this is no longer this result valid if both are not having the value 0 at the point a. That is very important. And g prime is not equal to 0, that is very obvious from here, because if g prime is 0, then we cannot divide it. Okay. So, that is why the condition is taken g prime a is different from 0. Okay. Now, here we have assumed the function attains the value 0 at the point a, and the derivative of the function exists at these points, is it not? Then only we can find the value. If the derivative or the functional value at the point a is not defined, but the limiting value is obtained, then also we can apply the result, and that is given by the L'Hospital's, and that will be known as the L'Hospital's rule first. In fact, first is very important, other rule is just a extension case. So, that is let a and b are two real number which may be real number which may be infinity or minus infinity also, and let f and g be differentiable f and g be differentiable on the open interval a b such that the derivative of g does not vanish anywhere inside this interval a b, that is non-zero for all x belongs to. Now, suppose that the limit of the function f x when x tends to a plus is 0, which is the same as limit g x when x tends to a plus, both are having the limiting value right hand limit exist and equal to value 0. Let it be 1. Then the result says if this condition, if limit of f x over g x, f prime x over g prime x when x tends to a plus, if the limit of their ratio of their derivatives exist and is a real number L, then the limit of the f x by g x when x tends to a plus from the right hand side will also exist and will be having the same value as the limit of f prime over g prime is there when x tends to a plus. The second is, if suppose L is infinity or minus infinity. So, if limit of this derivative f prime x over g prime x when a tends to a plus is suppose L, which is either in minus infinity or plus infinity only, then the limit of this f x over g x when x tends to a plus will also be minus infinity or plus infinity depending on L. Okay. So, this is what is known as the law. So, what this L-Splitter's rule says is that if we assume the differentiability of the function, but not necessarily at the point A, then the behavior of the limit of f x by g x and the behavior of the limit of f prime x over g prime x will be the same. That is, the limiting behavior of f prime over g prime will be the same as the limiting behavior of f x by g x, whether L is finite or infinite or minus any real. Now, here second point which we also want to discuss, though I have taken the limit a plus, means the interval is this a b and we are taking the limiting value from the right hand side, but the same result continue to hold good when we take the limit b minus or a minus, suppose it is completely defined, or limit exists. If the function has a limit at the point x equal to a, then we can replace a plus by a like this. So, if the limit of f prime over g prime at x tends to a is L, then the limit of f x over g x over x tends to a will also be L. So, in case limit f x as x tends to a exists and 0 and equal to the limit of g x when x tends to a, when f and g both are having the limit, I am not taking only the right hand limit, let us limit exist. Then if limit of this ratio f prime over g prime x when x tends to a is equal to a exist, then limit of their ratio will also exist and will be the same as L. It means the proof will remain the same whether we replace a plus by a or a plus by a minus, provided the limits are there. If the left hand limit exists, we use this. If the limit exists, we use this. If the left hand limit exists, right hand, then this left hand limit exists, then a minus and like this, but the result continue to hold good. So, we will establish this proof when the right hand limit exists, okay? And for others cases the proof is the same. So, let us see the proof. Now, let us take an alpha beta lying between a and b. Okay? Now, since the function g since G, which is given to be differentiable over A B, since G is given differentiable over A B and G prime x is not equal to 0. So, this automatically implies the value of G beta will be different from G alpha. Why? The reason is otherwise by Rolle's theorem, if a function G which is continuous over the closed interval a alpha beta, differentiable over the open interval alpha beta, G is given differentiable over alpha beta, and if the end point alpha and beta the values are same, then there will exist a point C lying between alpha and beta such that that is A and B, such that derivative of G at the point C must be 0, which contradicts our assumption that G prime x never vanishes for any x belong to the interval A B. So, always this result will be true, that G alpha is okay. Now, take the interval alpha beta, apply Cauchy mean value theorem for the function f and g over the interval alpha beta. So, what the mean value theorem says, if f and g both are continuous over the closed interval alpha beta, differentiable on the open interval alpha beta, then f of b minus f alpha divided by g beta minus g alpha is the value of the f prime set C or f prime u divided by g prime u for some u in lying between alpha and beta. So, by mean value theorem there exists an u belongs to alpha beta such that f beta minus f alpha g beta minus g alpha is the derivative this thing for some u. Okay. Let it be 2. Clear? This is by deal. Now, let us take the case 1, say A. What A? It is given limit of this is given limit of f prime over g prime when x tends to a from the right hand side is L. This is given. So, given limit x tends to a plus f prime over g prime derivatives is L. Okay. So, given. So, let us take so if L is given, that is if L is known which is in R, and let epsilon and if epsilon greater than 0 be given as some positive number. Now, limiting value of this is L. It means when the point A close to some interval, say AC I take. So, whatever the point x in between this, the limiting value of this prime is L, means difference is very small. So, this lies between L minus epsilon and L plus epsilon. So, we can say there exists a C belonging to the interval A B such that f prime x over g prime x lies between L minus epsilon and L plus epsilon for all u. Let us be this u. So, let us take the all u, okay, all u, for all u belongs to the interval A C. Okay. We can find the neighborhood of right neighborhood of A, where if we take any point in that right neighborhood of A, this condition will be satisfied. Okay. But f prime u over g prime u we have already find out from there, is it not? So, from 2 we have discussed this, from 2 f prime over g prime is this. So, substitute this value. So, use 2 Hence, from 2 we can say L minus epsilon L is less than f beta minus f alpha over g beta minus g alpha, which is less than L plus epsilon L for A less than alpha less than beta less than equal to c. Now, take the limit, take limit as alpha tends to a plus, because a plus this limit will be 0, is it not? So, this limit will be 0, this will be 0. So, what we get is, so we get L minus epsilon L is less than equal to, when you take the limiting equal to sign may also come. So, this is less than equal to epsilon L, and this is true for all beta belonging to the interval AC. Therefore, this shows the limit of f x by g x when x tends to, because this limit is not, when this one is there. So, limit beta tends to a. So, when you take x in place of beta, I am taking x. So, x tends to a plus is also L, because here let beta approach to a from the positive side, that is equivalent to say that x approach to a plus, where x belongs to this interval. So, this shows this. Okay. The second case, when L is plus infinity, L is plus infinity, and if m be choose greater than 0 is given, because the limit is given to be L, which is infinity. So, what do you mean by this? It means that there exists a C belongs to A B, because this is given, this is given, this is suppose infinity. It means when point is closer to A in the neighborhood, right neighborhood of A, then this limit can, this value can exceed any positive number. So, I am taking m to be greater than 0, then a number u can be obtained. There exists C such that for all u this condition is satisfied, is greater than m for all u belongs to AC. Okay. And but since epsilon is arbitrary number, this then from here this implies f of b, this implies again substitute 2. So, f of beta minus f of alpha divided by g of beta minus g of alpha is greater than equal to what? M is greater than m, strictly greater than m for all alpha and beta lying between this bond, okay, in the right neighborhood of A. So, take the limit as alpha tends to A plus, and immediately we get the f beta over g beta is greater than equal to m for all betas belonging to AC. And this shows, since m is greater than 0 is arbitrary large number. So, limit of this f beta over g beta when beta tends to A plus will be infinity, and that is full. The other cases follows in a similarly we can show for other cases. Okay. So, that is prove the results. Let us see the use of this. Suppose I take the example, find the limit of sin x over under root x when x tends to 0 plus. Now, if we look here, the function f x is sin x, g x is root x. When x tends to 0, the limit of this basically f of 0 is 0, g of 0 is 0. So, value at the point 0 is 0. So, when you take the limit, it comes out to be the 0 over 0 form, but the root g x is not differentiable at 0. So, the first theorem which we have shown it will not be applicable. However, we can apply the L'Hospital's rule, because g x is differentiable in the open interval 0 to say any 0 to infinity and g prime x is not 0 on 0 to infinity, and f x is also sin x is f x is also differentiable. So, there is sin function is differentiable and like this. Okay. So, we get, and this is not required, this is not required, okay, up to here only. So, we can apply the L'Hospital rule. So, L'Hospital's rule says that limit of this will be the same as the limit of their differentiation derivatives. If we differentiate the numerator and denominator separately, what you get is this limit will be the same as the limit of this, that this one, but this is equal to limit to root x cosine x as x tends to 0 plus, and now this is dominated by x. So, the limit will come out to be 0. So, answer is 0. Another example we can say, suppose I take the this example, say e to the power x minus 1 and both side. Okay. Take this example, log a e to the power x minus 1 over say x square, limit x tends to 0, x tends to 0. So, it is x minus 1. Let us take this also, okay, x minus 1. So, what happened when you take x tends to 0, it is 0 over 0 form, because e to the power 0 is 1 and this is 0. So, it is indeterminate. Both the function f and g satisfy L'Hospital's rule. L'Hospital's rule. Okay. So, apply it. So, by L'Hospital's rule, differentiate the numerator and denominator separately. So, if I differentiate e to the power minus and denominator will give, and then take the limit. So, by L'Hospital's we get this thing. This limit is the same as this limit, but again it is 0 over 0 form, because again 0. So, again apply the L'Hospital's rule. We can repeatedly apply the L'Hospital's rule so far the conditions of the L'Hospital's rule are satisfied. So, if we apply again, then you get e to the power x by 2 limit x tends to 0. Now, this is half. So, answer will be half. So, this is one. Then other forms, let us take L'Hospital's rule. Here is slightly different than the previous one. Let minus infinity, which is less than the case which is not covered in the previous one, minus a is less than equal to a, less than minus infinity, less than equal to a, less than b, less than infinity, or maybe at the most equal, it may be infinity also, and let f and g, f g v differentiable, f and g differentiable on the interval a b such that g prime x is not equal to 0 for all x belonging to the interval a b. And suppose that limit of g x when x tends to a plus is infinity or maybe minus infinity. Okay. Then if the following condition holds, then if limit of f prime x over g prime x when x tends to a plus is suppose L belongs to R, a finite number, then the limit of f x over g x when x tends to a plus will also be L. So, here the case is this: if f and g are differentiable, okay, and the limit of g x is infinity or minus infinity. Suppose I take plus infinity and the derivative of g does not vanish anywhere in the interval, then if the limit of their derivative exists, then the limit of their ratio will exist. So, here it is silent about the f x whatever the f x value may be, okay, this will be L. Is silent on the f x, but it is defined and different. So, it is finite value defined in this, okay, and this limit will be this one, okay, silent about this. Second part says if limit of x tends to a plus f prime x over g prime x is say L, which is either infinity or minus infinity, then the limit of their ratio f x over g x as x tends to a plus will also be L. Okay. The proof I am just dropping, because the proof based on a similar lines, as a, except that here just I will give use the same lines, use the similar lines as in previous case, and then and also use this the fact that limit of g x x tends to limit of g x as x tends to a plus is infinity. So, case 1 when you take the infinity, suppose I take the infinity, minus infinity will deal. So, if this it implies that there exists, we can assume, we may assume that the value of g at some point c will be positive, because it is going to infinity. So, after certain state it will cross 0. So, the a point c will come where it is greater than 0, and hence the g of c by g of alpha, when alpha tends to this when as alpha tends to a plus, and also the fact that this thing when alpha tends to a plus. So, condition is given that if g x as a plus is infinity. So, this will go to 0. So, fact that g x over alpha as alpha is tending to 0 as x alpha tends to a plus, because this tends to plus infinity and this is positive. So, this will go to infinity. Therefore, we may assume that 0 less than g c over g alpha, which is less than 1 for all alpha which lies in the right hand neighborhood of a. Okay. Now, using this fact and similar lines, we can show the previous, just from the third proof of this, as we have seen, we can go the proof which. In fact, from 3, if you remember, this was third. Yeah, this was the case when f alpha ends up. So, beta equal to c, if I put it, then we get from here say third here. So, in third, if I put beta equal to c, and then consider this, we get the L minus epsilon multiply all side by g c over g alpha, because this is positive, is less than f alpha by g alpha minus f c by g c is less than L plus epsilon into 1 minus g c by g alpha. In fact, this. So, and from here, as alpha tends to a plus, we will get this limit will exist, and limit will come out by calculations. you will get it limit to be greater than or equal to 2 epsilon L less than or equal to L plus 2 epsilon L. So, limit of this will be the same as this. I am not giving the detailed proof, but you can work out and get the results. Okay. So, because this time is not permitting for that, we wanted to have some more results here. Okay. So, let us take the other determinant forms, other indeterminate forms. So, case by case let us take, say first case is infinity minus infinity. I will give by example, seeing that a case of this where infinity minus infinity type. Okay. So, say for example, let I is the interval 0 pi by 2 and consider the limit of this as x tends to 0 plus 1 by x minus 1 by sin x. So, when you take x tends to 0, it is of the form infinity minus infinity. So, how to solve find out the value? What we do is we take the LCM. So, limit x tends to 0 plus, this is the same as x sin x minus sin x minus x. Now, it reduces, this is infinity minus infinity, now it is 0 by 0. So, apply the Hospital's. So, when you apply the Hospital's rule, differentiate the numerator and then differentiate the denominator. So, we get sin x plus x cos x and take the limit as x tends to 0 plus. If this limit exists, then limit of this will be the same as this. Now, x tends to 0, it is 0, again 0, so it is again 0 over 0, so on. So, further apply the L'Hospital's rule. So, when you take the, because all the f x and g x satisfy the conditions of L'Hospital's. So, we get x tends to 0 plus cosine x is minus sin x divided by say cosine x and then x. So, again cosine x then minus x sin x. So, when you take the limit of this, what you get is x tends to 0. So, that comes out to be now 0 over 2. So, this is 0, answer is this. Okay. Second case is say 0 into infinity type. Suppose I want to take the limit of this x tends to 0 plus x of ln x. So, when x tends to 0, it is 0 into minus infinity, that is 0 into infinity type. So, how to get it? This one is, what we do is we put it this in the form of 0 over 0 or infinity over infinity. So, if I take the ln x divided by 1 by x as x tends to 0 plus, then it is infinity by infinity type. Okay. Of course, minus infinity makes no difference. Then apply the L'Hospital's rule now. So, once you apply the L'Hospital's rule 1 by x and here denominator we get the minus 1 by x square as x tends to 0 and then when it comes up you get the value 0. So, it is coming to be 0. Third case, when it is of the form say 1 to the power 1 to the power 0, 1 to the power 0. For example, suppose I take the limit of this 1 plus 1 by x as x tends to infinity power x, 1 to the power infinity, sorry, x tends to infinity, okay, 1 to the power infinity. So, it is when x tends to infinity, this is 1, this is infinity. So, infinity to the power infinity. So, what we do is we consider this L limit L, take the log. So, when you take the log, it is comes out because limit is a continuous function, log will go inside and we get log 1 plus 1 by x and x tends to infinity. So, basically when x tends to infinity, it is infinity into 0 type. So, this can be put it again either 0 over 0 or infinity over infinity type. So, we can put it this as 1 plus 1 by x divided by 1 by x limit x tends to infinity, that is infinity over infinity type, and then apply now L'Hospital's rule. So, if we apply the L'Hospital's rule, what we get, differentiate the numerator. Numerator differentiation will give 1 over 1 plus 1 by x, and then derivative of this will be minus 1 by x square, and then minus 1 by x square. So, and then take the limit as x tends to infinity. So, basically this limit comes out to be 1. So, since log of L is 1, is it not? Log of L is 1, therefore, so log of L is 1, therefore, anti-log of this will e to the power 1, that is e. So, answer is basically e. Then next case is for when it is of the form say 0 into infinity 0 into 0 type, 0 power 0 type. So, for example, if we take the limit x to the power x when x tends to 0 plus. So, it is 0 to the power 0. Again in this case take the L log, and when you take log, this problem is reduced to the case when it is 0 into infinity type. So, just like a previous one, we can take it log x by x as x tends to 0 plus, then apply it is infinity 1 by x. So, infinity over infinity. Now, apply the L'Hospital's rule. So, when you apply the L'Hospital's rule, differentiate the numerator and denominator separately and take the limit when x tends to 0 plus, and this limit will come out to be what? 0. So, the L will come out to be e to the power 0, that is one answer. Then another case 5th, which is of the form say 1 to the power say again what form left now, infinity minus infinity we have taken, and then let us take another case is limit of this x tends to 0, 0 into minus infinity x log x, that we have already considered. So, I think this is all forms we have discussed, is it not? So, let us see. Okay. So, we can say another form infinity, and let us take one more example, then what we want. Suppose I take 0, say 1 minus x, x tends to 0, okay, into say 1 to the power infinity. So, let us take the 10x, no, cot x, and x tends to 0. So, what this is the 1 to the power infinity. Okay. So, what how will you do it? Take L and then log L. So, log L will be equal to what? Cot x into log 1 minus x, and x tends to 0 plus. So, cot 0 is infinity, this is 1 0. So, 0 into infinity, then again you can take log 1 minus x divided by 10 x, and x tends to 0 plus. So, it is 0 over 0, apply L'Hospital's rule, and we get from here is differentiate numerator, differentiate denominator, take the limit when this goes to 0. So, when you take the 0, upper limit comes out to be 1, and this is sec is also 1, the limit will be 1. So, L will be equal to e to the power 1, answer will be this. So, that is what is shown. So, it is almost we have completed this one. Now, let us come to the Taurus theorem. The Taurus theorem, it is an extension of the mean value theorem. In mean value theorem, we give the relation between the functional value and its first derivative, whether it is a Lagrange's mean value theorem, f b minus f a or b minus a derivative of the function, or maybe the Cauchy mean value theorem, where the two functions f and g are there, and then we get the relation between f, g and their derivatives. Taylor's theorem is an extension of the mean value theorem, where we have a relation between f and its higher order derivatives, and is basically used to approximate the functions with the help of the first few terms of the Taylor series or Taylor theorem. What this theorem says is, let n belongs to capital N, okay, and let I is the closed interval a b, and let f is a mapping from I to R be such that f and its higher order derivatives say up to order n, f prime, f double prime up to f n, the nth order derivatives up to r continuous on the interval I, and that the n plus 1th derivative exists on the open interval a b. Now, if if x naught is a point in the interval I, then for any x belongs to I, there exists a point C between x and x naught, such that f x can be expressed as f x naught plus f prime x naught into x minus x naught plus f double prime x naught over factorial 2 x minus x naught whole square and so on, and then plus f n at the point x naught divided by factorial n x minus x naught to the power n plus the remainder terms r n x, where r n x is given by f n plus 1 c over factorial n plus 1 into x minus x naught to the power n plus 1, and this is known as the Lagrange's form of the remainder. So, the function f is such which is differentiable and continuous up to say n plus 1th order time, and n plus 1th order derivative exists in the neighborhood of the point x naught, then there exists in the open interval a b, of course, and the neighborhood of the x naught. Then there exists a point C where the expansion of the function f x can be written in the form of the series, where the first n terms of the series is the polynomials of degree n, and this term is called the remainder term, and it is known as the Lagrange's form of the remainder. Now, in case if the remainder R n goes to 0, then this same expansion is known as the Taylor series expansion for the function f x. Okay. So, we will discuss it next time, the proof of this. Thank you very much.